I get the sign that I should start. Welcome to the authors and welcome to all the people in the auditorium. It's my pleasure to do it again, having the authors here to answer questions. And so we can start with the first question. Alex, that questions go to your side. Are the chip scale pads harder to assemble compared to packaged pads?
Well, I would say that the chip scale parts are very small, and so they definitely are challenging from a assembly point of view if you're not using more advanced technology for assembly. The distance between the pads is smaller. It depends on the voltage rating, but it's not smaller than other ICs and package parts that you see today. Where we see the most challenging part is that you know, a lot of people are used to much bigger, old power components, and they're having to adapt. Now, we do have a new line of packaged products that should be very straightforward to assemble for anybody.
Thank you, Alex. This question is addressed to Keysight. What is the biggest challenge to dynamically characterize power modules compared to discrete power devices?
Yeah, this is Mike Hawes. So I'm a solution consultant with Keysight, and you know, the big challenge there is moving to testing high side and low side with dynamic rejection that's needed, the common mode rejection on the high side. It's quite a bit more difficult to get good measurements, VGS, VDS, and even if you so choose a current on the high side for characterizing. That's difficult. What we've also seen is there's lots of changes in the packaging for modules. They're trying to reduce the parasitics. And so that continues to be a moving target and will continue to be in the foreseeable future. So fixturing and connecting to the module is also a significant challenge.
Thank you, Mike.
Yep.
The question goes to monolithic power systems. What applications are isolated gate drivers useful for?
Well, hi. My name is Tomas
Hi.
Hudson. I'm an applications engineer here at MPS. And so isolated gate drivers are useful for a wide variety of applications, basically those that require higher voltages, as we're seeing now in the evolution of these applications, such as for EVs, onboard chargers and inverters, or for renewable energies, or also for high power supplies like for server and telecom applications. Basically, all these applications are now moving towards faster switching, higher voltages, and this means that we need to make sure that we're properly protecting our control circuitry. So that's one of the uses for isolated gate drivers. Especially, for example, topologies such as the totem pole PFC topology, which is really, really useful in these sorts of applications where we have hard switching and high voltages. There we need to really make sure that we're using isolated gate drivers, especially in the high side MOSFETs, for example.
Thank you, Thomas. Are all GaN transistors less expensive than silicium MOSFETs? That's,
I think that's probably for me.
That's for you, Alex.
And the answer is no, not all, but a large number of them are. For example, EPC's 100-volt MOSFETs and 200-volt MOSFETs are typically priced lower than MOSFETs. Our GaN devices at 100 volts and 200 volts actually cost less to produce than MOSFETs. And we've priced them right in the middle, not the cheapest, but not the most expensive. I can't speak for high voltage GaN devices compared to MOSFETs, but I do know that GaN devices in the 100, 200 volt range right now are not only price competitive, very often they're cheaper, and they are only getting less expensive with time, whereas MOSFETs in that range are pretty much at the limits of their technology.
Thank you, Alex. Do you make high-side ID current measurements? That's to Keysight addressed.
Yes. Yeah, thanks for that question. And that is a difficult measurement with the common mode rejection, as I was talking about previously. Often a lot of people are using Rogalski coils or some others that the bandwidths aren't significant in that technology, or at 30 megahertz, maybe up a little bit more. I know there's some that are shooting for 50 megahertz. But right now, currently with their solution, we are looking at using an isolated channel and a shunt that provides more parasitic in the power loop, and so we were a little concerned with that, but we're doing some experimentation and looking at trying to provide that so that that can be synchronized with the other measurements. So challenge for sure, but we're having it on our roadmap and taking a look at it. Yeah, thank you.
Thank you, Mike. How is the capacitive isolation implemented in isolated gate drivers? That's the question to monolithic power systems.
So, so we implement capacitive isolation, which, as the term indicates, right, we use capacitors to separate, to act as an isolation barrier. So the way it works is there's two levels of isolation, so to speak. So we'd have basic isolation and reinforced isolation. Reinforced isolation is basically the same as, say, we have a wire and we cover that in plastic for isolation. Reinforced isolation would be covering that plastic in another plastic. So if the exterior isolation layer breaks, then the system or the user is still protected by the first layer. So we use two capacitors in series, and that's how we get up to 5 kilovolts RMS isolation in input to output, right? So the way this is implemented, we have two dies referenced to two separate grounds, and so the isolation is that the difference between both grounds can be up to 5 kilovolts without there being any current flowing from one to the other, right? So the way this is implemented is on the input. In the article, there's a sort of a schematic of how the isolated gate driver, sort of a block diagram. So how it would work is the PWM signal from the controller enters the IC, and then there is a modulator which converts the signal into a high frequency that can cross over these two capacitors. These capacitors, there's one on each of the two dies, which are connected by a bond wire, and the capacitor is basically built within the die. That's why capacitive isolation can be, since it can be implemented within the same die, it saves up a lot of space, and it also ensures that we can, also implement filters very closely to minimize the propagation delay and to maintain very high isolation within a very, very small package. But yeah, so the way it's implemented is we use the metal one layer, for example, and then the top layer of the die, and in between it's just silicon oxide that acts as a dielectric. And because the distance between both conductors is very big, well, very big for microelectronic standards, right? It's in the microns range. Then the capacitor is very, very low value of capacitance. So I think it's around or less than 100 femtofarads. So that means that the way we transfer the signal from one side to the other, it means we have to modulate it at quite a high frequency for it to go through the isolation barrier. Then in the secondary, there's a demodulator which recovers this signal and converts it and shifts it to a level where we can actually drive the power switches.
Thank you, Thomas. So GaN devices have a much lower thermal resistance compared with MOSFETs, but they are also much smaller. Does that mean it is harder to get the heat out even with the lower thermal resistance?
I think that the thermal resistance is the key. And GaN devices are about 10 times lower thermal resistance than a packaged MOSFET. So they're 10 times smaller, they have 10 times lower thermal resistance. So for about the same amount of power dissipated in the device, you can get 10 times higher power density. But GaN devices are more efficient, so they tend to generate less power. So you get an additional benefit in terms of power density. Plus, we've worked with thermal insulating material vendors over the last couple of years and have more than tripled the thermal conductivity of very low-cost thermal insulating materials. One other very important factor is our back surface of our GaN devices is at low potential, at source potential. So very often you don't need an insulator between that and the heat sink, and therefore you can get thermal materials that are even 3 and 4 times more efficient than the most efficient thermal insulating materials. So by and large, we've seen phenomenally efficient thermal systems with our GaN devices. And we also have simulators on our website. We wrote a chapter in our book about it.
Thank you, Alex. So we're ready for the next question. It's to Keysight. Does the PD 1550A also test discrete devices?
Yeah, good question. We've had a PD 1500 in the industry for 3 or 4 years, and doing both silicon carbide, IGBTs, and GaN for characterization. 1550 is focused on modules, but yes, it will be a superset solution where you will also be able to test discrete. So all of the capabilities that we currently have in the 1500 today will be available and are on the roadmap. Today it's focused on modules, but that capability is, you know, within the next year you'll have that capability for discrete, and then you'll have that system that can do both.
Thank you, Mike. It's to monolithic power systems. Are isolated gate drivers designed for specific technology, SiC, GaN, or silicon, or can they be used universally?
Well, our isolated gate drivers have bias voltages that go from 6.5 volts, I think, to 30 volts. So we can then bias a wide range of technologies, so including silicon carbide and GaN. Yeah. So the simple answer is yes. Yeah, that's it.
Okay. Thank you, Thomas. It's to Alex again. Going to higher frequency is the main advantage of GaN devices. Don't the magnetics limit the performance at higher frequency? How about EMI?
So yeah, going to high frequency is one of the advantages of GaN. I mean, we can't forget the fact that the devices are much smaller, and you know, as we talked earlier, they're competitively priced compared to MOSFETs. When you're looking at applications like DC to DC conversion, magnetics is the key limiter. Forgive me, I'm in an airport, so these announcements will happen. But magnetics has gotten a lot better. So we're seeing, for example, the sweet spot today for DC to DC conversion is around 1 megahertz, whereas with MOSFETs, it was really in the 100 to 300 kilohertz range. Now, we also have applications that are at much higher frequencies than that. They tend to be a little bit more difficult. Now, there's also the question about EMI. And the thing about GaN devices, they switch faster, but EMI isn't really related to how fast you switch the device. It's related to things like ringing, overshoot, antenna effects in your layout. Now, GaN devices allow a much smaller layout, and therefore you have less antenna effect. Number two is, since the chip scale packages have no package, there's no internal inductance, and internal inductance causes a lot of ringing, which is a big source of EMI. The other effect is GaN devices do not have a body diode, and diode recovery in a hard switched application is a huge source of EMI. So with GaN devices, we still have the EMI that comes from a leading edge and a trailing edge of a switching transition, but we can minimize the overshoot ringing effects, which tend to go with the square of the voltage of the overshoot, and we also eliminate the effect of the diode. So overall, we're finding much quieter circuits.
Alex, thank you for your answer, and we're going to the next. It's again to monolithic power systems. What effect does the isolation barrier have on the propagation delay of the driver?
So the propagation delay sort of is in a trade-off, basically with more than isolation. It would be with CMTI, which in case anybody is unfamiliar with it, common mode transient immunity. So when we're switching, especially when we're switching at high voltages and high power, then there are certain spurs that are generated in the switch node, which can then be which then enter the driver, cross the isolation barrier, and wreak all sorts of havoc in the circuit, such as shoot through, for example. So the thing is, in order to eliminate this CMTI, there's several mechanisms that we can use, but any of the circuitry that we use to eliminate CMTI will unavoidably add to this propagation delay. So if the propagation delay is in a trade-off with the CMTI, we can only reduce it so much without affecting the CMTI to a point where for example, our isolated gate drivers guarantee a minimum CMTI of 100 kilovolts per microsecond, or 100 volts per nanosecond. So going down below the, I think now some of our isolated gate drivers are rated at 50 nanoseconds propagation delay, but now it's being pushed down to 20. But of course, below that, then we start to find, lots of issues with how we eliminate all of the potential noise and the CMTI within the driver as well. So it's as in everything in electronics, right? It's a trade-off.
Thank you, Thomas. Here comes our last question from the auditorium. It's addressed to Alex. Higher DVDT in motor drives can cause reliability problems in motor drives. Is that a problem when using GaN transistors at higher frequencies?
So I think what this question is aimed at is with very high DVDTs, there have been pinholing of motor windings, of the insulation between motor windings in motors typically driven off of the AC line. For our GaN motor drives, we're really working on battery-operated systems, 96 volts, 48 volts, 36 volts, and 24 volts, where the DVDTs are nowhere near the region where they can cause pinholing in the motor insulators. Also, GaN devices tend to switch in a slightly softer way than a MOSFET, which seems counterintuitive since they switch so much faster. but where the transition is at the beginning and the end of the transition cycle, it is actually curved slightly, and it actually reduces the amount of stress on a motor winding. So the answer really is no, it's not a problem. Also, when you go to higher frequencies in motor drives, you can eliminate a lot of the acoustic noise problems that you have in motors. So we're seeing a lot of these battery-operated systems going from the typical 20 kilohertz up to 100 kilohertz, and they're having less EMI, less acoustic noise, and certainly no reliability issues in the motor windings.
Thank you, Alex. We get more questions going. Just a second, my backstage is converting them to show them on the screen. They just came in the moment. Here we go. It's again you, Alex. I can see that there are only a few GaN devices with integrated drivers. Is there still an advantage to drive directly GaN devices with our own circuitry, and what are they?
So there is a growing ecosystem of drivers for GaN devices, both half-bridge drivers, which have level shifters in it, as well as direct drivers. We also have a family of GaN devices with integrated drivers. We also have a family of monolithic half bridges with drivers and level shifters. So this is an evolving story that's getting better and better. In terms of directly driving devices, our small devices, I would say those devices below about 1.5 millimeters on a side, can actually be driven directly off a logic gate. At very high speeds in the multi-megahertz range. So in many cases, you actually don't even need a driver whatsoever. Just drive it directly from logic, something you couldn't even dream of doing with a MOSFET with the same power levels.
Thank you, Alex. It's a question to all of you. For high VDT, could the isolated gate driver and isolated DC-DC converter fail because of the capacitive coupling?
So if I can start on this.
Thomas, go ahead.
So the capacitive coupling caused in the DC-DC converter with high VDT, that is what we aim to avoid with the CMTI. So we aim to avoid a loop being generated through the isolation barrier, and then charge being accumulated, for example, in the gate of one of the high side MOSFET, for example. So if charge is flowing in a loop through the drivers and through the grounds, and this charge gets accumulated in say when the low side MOSFET is closed, and the charge accumulates on the high side MOSFET or switch, in this case. Although, so if it accumulates at the gate, then yes, it could open the gate and close the switch both at the same time, causing a shoot-through current, which could potentially make the device fail. This is what we avoid with CMTI. So when we have CMTI levels, so immunity to transients in the common mode, which are above 100 volts per nanosecond, this means that in most applications, by using isolated gate drivers, you're perfectly secure with this sort of coupling.
Thank you, Thomas. Another question is coming up. Another second. Here we are. 800 volt applications using 650 volt GaN in series connected.
Yeah, so maybe I can take that. I think that in 800-volt applications, which is becoming a big topic because of the shift on electric vehicles from 400-volt buses to 800-volt buses. A 650-volt device obviously can't do an 800-volt bus unless you do something, either put devices in series, which is probably ill-advised, or use a multi-level converter. A multi-level converter can actually, step up level by level, and so you would, whereas a half bridge is a 2-level converter, if you go to a 3-level 650-volt devices, you can handle barely an 800-volt bus. Then there's the question of, well, is that the most efficient configuration?
Absolutely.
And there's certainly a lot of work on that going on. So it's a very interesting space. Do you use silicon carbide? Do you use multi-level GaN devices? Do you make high voltage GaN devices? And I think that one of the things that's interesting is that there is a recent figure of merit that's come out from University of Texas Austin that shows that the optimum spot, the best spot, is an N-level converter with about 200-volt devices for a variety of reasons. It has to do with the on resistance of a 200-volt device versus a 600-volt device, whether it be in silicon carbide or GaN. So we're looking at that very closely, and it's going to be a very interesting place to watch. What is the best technology for an 800-volt EV bus?
Alex, I see the amount of devices. If you go to multi-level, you have, by the amount of levels, more these devices that all have to be in the failure calculation of the system. So from my understanding, as an engineer, use as less as possible devices to minimize the failure calculation. That's what an older man has in mind.
But there's an interesting twist to that. When you go to high current applications like electric vehicles, you're actually doing many devices in parallel. So if you have a much lower on resistance GaN device, you need fewer of those in parallel. So we've actually found that there are interesting crossover points. For example, a 500 ampere 800-volt bus, depending on some of your assumptions, might need 130 IGBTs, but it needs also 130 200-volt GaN devices. And the reason is because you have fewer in parallel of the GaN devices because each one is so much lower on resistance. Where you have the complication is obviously in the control loop, it's more complex. Also, you have more capacitors. And that, of course, could add to the cost and complexity as well.
Thank you, Alex. Let me ask. My backstage said, no more questions. So I will say thank you to the authors and thank you to the auditorium. Have a great afternoon, morning, wherever you are in this world, and enjoy the rest of the day. Today it's a little bit cold here. Otherwise, I would say I would go to the beach. So,
thank you, Bodo.
Thank you, gentlemen, and enjoy the day, and looking forward to our next event.
Thanks, everybody.